Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSC in Ministry of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about a different shortest path problem. So, shortest problem is nothing but finding the shortest path between the pair of vertices in the graph. So, how can I able to find the shortest route between the 2 points on the road map is the question. So, for this kind of problems, we're going to be model a problem into a form of graph, and the roadmap is nothing but the weighted graph, especially not a simple graph or directed graph. So if I'm going to have the graph like this, so how can I able to find the shortest path between the different types of vertices in the graph? Assume that this should be the different kind of cities. If it is, then what should be the shortest path for reaching from one city to another city? So I assume that the vertices should be considered as the cities, and edges should be the road segment that is connected between the cities in between them. And then the goal is to find the shortest path between the pair of vertices here. Uh, Let me explain this. So if I'm going to have if I want to reach from A to B, so one is the shortest path. Otherwise, I can also reach from one A to E and then A to B also, but it should be cost around 4 plus 3. Otherwise, I can also reach from A to D and then D to C and then C to D also. So it should be, so A to D it should be 2 and D to C 6 and plus 2, that should be total cost is 10 in this case, and here it should be scale 7 and here in this case 1. So it should be the shortest path, then it should be A to B only. So like this, we're going to be find the shortest path between the pair of cities here. So next one I'm going to see, suppose the input should be weighted directed graph, and the weight of the path is nothing but the sum of the weights and the along the vertices in the graph here, and the shortest path weight from Q to B is the minimum of this. So if there exists a path from, you have to represent it, otherwise it should be infinity. So what are the different kinds of variants of shortest path? So we're going to have two types of shortest path here. So first one is single source shortest path and single destination shortest path. So single source shortest path is nothing but finding the shortest path from the given source vertex to the each vertex. Okay, so single source shortest path means that, so we have to find the shortest path from the given source vertex to the each vertex. And single destination shortest path means we are going to have only one source and one destination. So how do we find the shortest path between this, and reversing the direction of each is nothing but the single source. So if I'm going to have, so single source means in single source what is the shortest path from A to B, A to C, A to D, and A to E like this. But here in this case, what should be the shortest path from A to E only? So some other variants of this shortest path is the single pair shortest path. So that means we are going to find the shortest path from U to U, U to V from the given vertices. And all pair shortest path is now also there. So for this, find the shortest path between every pair of vertices of U and V. So if I'm going to construct a graph like this, so what should be the shortest path from A to B, A to C, and A to D, and similarly B to C, and then B to D, and then C to D, C to B, and C to A, and similarly D to A, D to B, and then D to C. Like this, we're going to find the shortest path between every pair of vertices. That should be the all pairs shortest path. So sometimes the graph may also have some of the negative weights. So what we can able to call this as negative weight cycle. So if such cycles are reachable from source, then it should not be properly defined. So what I'm going to say that is we have to be keep on around the cycle with this. We're going to get WS is equal to minus infinity. Suppose if I'm going to have S to A, so only one path in between them, then the delta of S comma A and weight of S comma A equal to 3 only. So suppose if I'm going to have S to be only one path, then I can able to substitute these values in this equation. And similarly, if I'm going to have S to C infinite paths, then I can able to have a cycle with a positive H weight. So that should be 6 minus 3. So negative 8 weight edges. So if it should be S to A should be infinitely many paths, then the cycle is going to have negative 8. So that should be 3 minus 6 is equal to 1. So we can also find the path from S to E with arbitrarily large negative weights. And if the delta of S comma is for minus infinity, then no shortest path should be exist between S to E. Similarly, S to F1. So similarly, if I'm going to have the path from S to F is to minus infinity and S to G also minus infinity, then you can able to say in this case also have to find this shortest point in case of running two cycles. So what is the cycle here? So cycle is nothing but a shortest path can also obtain a cycle. So negative weight cycles are going to have no cycles here because the shortest path is not well defined in this case. And positive weight cycles also going to be no because by removing the cycle we can able to get the shortest one. And zero weight cycle that means no reason to is that and you can also remove them to obtain a path with same weight. So cycles can be a shortest path between the cycles and negative weight cycle is nothing but we're going to find the shortest path and positive weight cycle means by removing the cycle and get the shortest path. And zero weight cycle means that should be no reason to use them and can also remove or obtain a path from the same. So what are the algorithms that are available for finding the shortest path? So first one is the Bellman-Ford algorithm. That means negative weights are going to be allowed and negative cycles reachable from source are not going to be allowed. And distress algorithm means negative weights are not allowed. And then the operation that are common in both should be the initialization and relaxation. So some other different kinds of algorithms that are available for finding the shortest path. So first one is that Bellman-Ford algorithm. So in this Bellman-Ford algorithm, we're going to have negative weights that are going to be allowed, and then negative cycles are reachable from source are not going to be allowed. So when it comes to the distress algorithm, so the negative weights are only not allowed. But in both the operations, the common thing is that initialization and then relaxation. So, what is the notation have to be followed for representing this shortest path? So, for representing the shortest path, we're going to have delta from S comma B, that should be the shortest path weight, and distance estimation. It denoted by D, okay, that should be shortest path weight estimate. So, initially dV should be infinity. So, whenever the algorithm is gone, then we should be get the delta of S comma B, that should be the shortest path weight. And pi of V is nothing but predecessor of V on the shortest path. Uh, if no predecessor, then pi of V should be null. Then pi reduces nothing but actually that should be the shortest path. Then how can able to initialize this shortest path here? So for this we have to be initialize a single source. So for each vertex single group, d of v should be infinity and pi of v should be null. And distance of the shortest path distance should be 0. So this should be the initialization here. So for each vertex in the graph, So that should belongs to B, and then make dv of this should be infinity first. V2 is equal to infinity, and d of v3 should also be infinity. Then make the I of v should be nil. So all page shortest one going to be solved. Shortest path is going to be strongly initialized single source. And next one is Bellman-Ford algorithm. So in this Bellman-Ford algorithm, mainly it is going to be used for single source shortest path problem. So it is going to be compute delta of s comma b and phi of a for all three belongs to. And it also allows the negative edge weights that can detect the negative cycles. And it should be returns true if no negative weight cycles are reachable, and returns false otherwise no solution exists. So all negative edge weights can detect these negative cycles, and it should be returns true if no negative weights are reachable from source. So the main idea is that in Bellman 4, each edge is going to be relaxed by mod of v comma over 1 times by making v comma over and passes over the whole edge set. And to make sure that edge is going to be relaxed exactly mod of v1 times, it puts the edges in unordered list and goes over the pi minus 1 times. So these are the edges that is going to be obtained from the Buda graph. So tx and ty and then xt via its values. So in first pass, we have to identify from the single source. So what should be the minimum weight here? So 6 or 7. So I'm going to be select 6 in pass 1 first. And in pass 2, what I'm going to say is from 6. So what should be the path here? So for this, the pass 2 should be minus 4 is the minimum one, and minus 2 is the next one. So since minus 4 is the better one, so I'm going to select this minus 4 next. And minus 2, so is the next one. So that's one from 1, it should be minus 2 is the next best one. So I'm going to select it. And from 4, it should be minus 3, that should be the pass 4. So initialize the single source and then go on repeating the values for each edge and do relax step, and for each edge also we're going to return false. So shortest path properties. So we also always have different kind of properties upper bound. So we always we have like this. So if I'm going to make the relax of x comma b in this case, then I can able to relieve this. So after relaxing, we're going to get this to be. So next one, convergence property. What is this convergence property? So if I'm going to have the source to a particular edge, it should be a path shortest path. Then d of u is equal to delta of s comma b at any common time. That should be relaxing edge, and the d of v is equal to delta of s comma b for all the time. That should be relaxing. So dv is equal to d of u plus u comma v. The value remains unchanged because it must have the shortest path. And path relax property, that should be, so p is equal to v naught vk, that should be the shortest. Then if we are going to relax in the order, so that should be even intermixed with other relations. Our next one is distress algorithm. So normally distress algorithm is going to be used for single source shortest path problem. So here no edge weight edges are going to be considered, and each edge is going to be relaxed only once and maintain to have two sets of vertices, and d of v is equal to delta of s comma b, and d of v should be greater than delta of s comma b. So according to distress algorithm, this should be the single source shortest path problem, and each edge is going to be relaxed and maintain the two set of vertices. So repeatedly we have to be select the vertex u, and that should be v minus x with minimum cost edge estimation, and then relax all the edges leaving u. So what are the steps we have to follow is that, so every time we have to be extract the vertices from the Q and then insert Q to U to S, and then relax all the edges that is relieving U, and then update it. So these are the steps what we are going to follow in distress algorithm. So first of all, you have to extract the vertices from the and then insert U, S, and relax the edges from U, and then update the Q. So in this one, so I want to find the single source shortest path problem. And so story mining. So first, I have to consider the single source, and then first I have to find what should be the shortest path that I need to do. So next one, I'm going to select this. So I'm going to eliminate this one, and next I'm going to choose the next one edge is 3. So 3 is going to be selected, and then 9 if I'm going to select. If it is going to select 7, there will be chance of getting the dog mode should be dog, and so here I'm going to consider this edge, and similar fashion we're going to work on the remaining edges, and this should be the algorithm for this trust one. So here also I'm going to be initialize the single source, and so while q is not empty, we have to execute the q of v times, and then we have to extract the x is equal to distance u, and for each vertex we are going to obtain delta of e. Then all page shortest path is nothing but this is the another kind of problem. So that means I have to find what is the shortest path from 1 to 2, 1 to 3, 1 to 4, and 1 to 5. Similarly, what should be the shortest path from 1 to 2, 1 to 2 to 5, 2 to 1, 2 to 4, and 1 to 3, like this also. So if I'm going to have the directory graph, and this should be the function, so I have to find the shortest path between the pair of vertices on the graph, and then as a result of n by n of the matrix, we are going to be pass the distance. So all the shortest path problem should be done something different. So once I have to find the shortest path from 1 to 1 versus, then I have to work it out. So what is the shortest path from 2 to 1, 2 to 4, 2 to 5, and then 2 to 3 also. So like this are going to be estimate this graphs also. So all prime shortest path run the Wellman for once the edge vertex. Then if I'm going to have no edge weights, then we can able to run distance algorithm, and then we're going to solve the problem with the estimate of V of 3 if no elaborate data structures are going to be found. Then application feasibility is that, so linear programming and feasibility program is there. So here we can able to obtain the objective function of linear equation, and then feasibility problem. So here the application is that linear programming is one of the main application, where because we're going to be consider list of experiments as max 1, C1, C2, and then C2, X2, and so on, Cn, Xn should be the objective function. So simplex is the common approach used to solve the above problem. So the special case of the feasibility problem is that, so all the constraint is going to have xj minus xn should be less than 1. So that means if I'm going to have x1 minus x3 equal to 3, or x1 minus x3 is equal to minus 2, and x1 minus x3 equal to less than or equal to 2. So by using this, I can able to substitute these values in the form of matrix here, and x1, x2, 3, and these are the values. And next one is that constraint graph. So constraint graph is nothing but which is going to assign one vertex at a time, and then one vertex each constraint with the weight. And if I'm going to solve this, so xj minus xa equal to pk. So what should be the value of pk now? So it should also include extra edges and vertices. to every to every other vertex. So this should be the application feasibility or application solution for the given data. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.